Hi, Mark. It's Glenn, and I just want to see if this format of presentation to you is going to be useful. Um, Suppose you have the aluminum atom and the oxygen molecule, and they're doing some electron transfer. What happens to the aluminum? Well, you've probably done this problem already, but here's how I would show you. There's the aluminum atom. You'll see that it's in group 3A, or group 13. That indicates that aluminum has 3 electrons in its outer shell. In other words, 3 valence electrons. So let me draw that out for you. Here we have aluminum and 3 valence electrons. 1, 2, 3. Now, the octet rule is something that describes the behavior of most atoms and when they do chemical interactions with each other. And it says that the atom would like to have 8 electrons in its valence shell, or its outermost shell. And in some cases, that means losing its outer shell completely, so that the outer shell is the next outer shell, the one shell in the inner direction. So, in effect, that means the octet rule says that the atom would like to have either 8 valence electrons or no valence electrons. So what's easier here? Is it easier to get 5 more electrons to get this 8? We have 3 electrons here. Is it easier to get 5 more, or is it easier to just lose 3? So this is the 3 that we have. Is it easier to lose 3 or to get 5? Well, 3 is a smaller number than 5, so it's easier to lose 3. Therefore, aluminum will lose 3 electrons. So aluminum will lose 3 electrons, and that's just about what they wanted to know. Let's look at the next one. How many electrons do you expect each oxygen atom to gain or lose in this reaction, and why? Right, so let's have a look at that. Now the oxygens are in a different group. Let's see, the oxygens here are in group 16, or 6A. Now that means that the oxygen has 6 valence electrons. Okay. Now remember that these guys are doing electron transfer. So aluminum's 3 electrons, they're getting lost. So if someone is losing electrons, then someone else must be gaining those electrons. So let's see how many valence electrons oxygen has. I've said it was 3 by looking at the periodic table, right? I'm sorry, I said it was 6. There's 1, 2, 3, 4, 5, 6. Notice that I filled in these dots in such a way so that I have minimum pairing going on. Let me do that again for you. 1, 2, 3, 4, 5, 6. So you see, I just imagine that there's a box around the oxygen, and I add the electrons, 1 electron per box side at a time. And when I have to pair, I pair. This technique just happens to imitate the behavior of electrons in nature. They don't like to pair, but when they have to pair, they will. Alright, so you see that there are 6 electrons, right? And if you add 2 more, you'll get 8. This is the electrons that we have. If we add 2 more, we'll get 8. Now, you could also get no electrons by losing all your electrons, but which is easier, to lose all your electrons or to just gain 2 electrons? 2 is a smaller number than 6, so it must be easier to do the 2 thing. So now, of course, we'll do the 2 thing. Now, that little arithmetic wasn't really necessary because we already found that aluminum will lose electrons. So if aluminum is losing electrons, then someone has to gain those electrons, and that someone will be oxygen. But now there's a peculiar situation here. Here you've got 3 electrons to be lost, but here you only need 2 electrons. 1 electron to go into this spot, and 1 electron to go into this spot. So there's going to be an extra electron, right? I'll draw the arrows for you. This electron will go into this spot, and this electron will go into that spot. So there you're going to have an extra electron here. So what can I do with that? Well, there's only one thing you can do, and let's get another oxygen. And the reason for that is this problem is only about aluminum and oxygen, nothing else. So the electron has to go somewhere, and if this problem is about nothing else, that means the electron has nowhere else to go. So you have to bring in another oxygen atom. So here's another oxygen atom with its 1, 2, 3, 4, 5, 6 valence electrons. There's a space here for one and a space here for the other, because remember, oxygen can take 2 more valence electrons to satisfy the octet rule. Here we are. The space is filled there, but look, I have a space left over here. How am I going to get an electron to fill this space left over? This problem is only about aluminum and oxygen, so the electron must come from, that's right, aluminum. Aluminum is the only thing around here giving away electrons, so it's got to be aluminum. Oh, but look, this is absurd, right? We have 2 more electrons to give away and no place to put them. But this problem is only about aluminum and oxygen. So you get the idea, right, Marc? You go there, and you go there. So that's what happens. In fact, the compound is aluminum 2 of those, and oxygen 3 of those, aluminum oxide. That is the compound. You can explain that, right? The question asks you to explain this. Explain this in your own words. How many electrons do you expect each oxygen atom to gain or lose? I've shown that. I've shown that the oxygen atom will gain, and I've shown that it will be 2 each, and I've shown you why. Now, here you have these folks asking for the x and the y in ALXOY. You've seen from the previous explanation that this is the formula. I think you can come up with the answer from there, Marc. And I wanted to let you know also, there's something that they haven't asked yet, but that is very, very important. And it is the following. When you have aluminum losing all of its electrons, aluminum becomes charged. And the reason is every electron here has a minus charge. So with these 3 valence electrons, aluminum is neutral. But if aluminum were to lose an electron, then it is losing negative charges. If you lose negative charges, then that ruins your balance. So that makes you have a positive charge because you've lost negative charges. So if it has lost 3 electrons, 1, 2, 3, it has lost 3 negative charges. That leaves aluminum with 3 positive charges. It is now the aluminum ion, aluminum 3+. And oxygen, of course, 1, 2, 3, 4, 5, 6. Having gained 2 electrons from from aluminum, having gained two electrons from aluminum, oxygen has 2 extra electrons, making its charge 2 minus, right? Because it has 2 extra negative charges. Now, it's a little confusing because the octet rule says that these atoms want to gain electrons or lose electrons, to have 8 electrons on the outside or no electrons on the outside. The octet rule says that this is desirable, yet this activity creates a charge, which is an unbalanced thing. Yeah, there are two different phenomena at play here. There's the octet rule, and then there's the charge. They're different things. So it is true that by following the octet rule, oxygen gets this unbalanced charge, 2 minus, but nevertheless, oxygen still behaves as though it wants to follow the octet rule all the time. So there's no need to be concerned about that apparent paradox. Here we have, you should probably also understand the Lewis dot structure. In the Lewis dot diagram, you have a more formal way of writing down in diagram form the mess of arrows that I had drawn for you previously. And that way is this. All the negative ions are enclosed by brackets. to emphasize the fact that these electrons now belong to this atom. And I've just used the word ion. Ion is just an atom with a charge. So this oxygen atom is now an ion because it has 2 extra electrons, giving that 2- charge. The positive ions, this aluminum atom is now an ion because it has lost 3 electrons. The positive ions don't have brackets because they don't have electrons that belong to them. They have electrons, of course, but they just don't have their natural valence shell of electrons. Right? So here you have 2 Als and 3 oxygens. This is the Lewis dot diagram. Now, your teacher might prefer for you to draw these components of this Lewis dot diagram all on a single line in order for you to make your paper neat. Some teachers, in fact, prefer for you to draw the Lewis dot diagram so that all of the positive ions are surrounded by negative ions, or vice versa, so that you never have the situation where there is a positive ion next to a positive ion, because in nature that would never happen. It just depends on the way your teacher prefers for you to have the work shown. That's the Lewis dot diagram. Here, let me write that for you. Sorry about that. That's the Lewis dot diagram. Okay. But that has nothing to do with number 3. That's just something that you're likely to see in the near future, if not already. Now, how would you describe the structure of solid aluminum oxide at the particle level? Because you've just seen ions, let me write that word for you, ions, you've just seen that aluminum and oxygen both become ions in order to form the compound aluminum oxide, because you've just seen that. It's probably useful for you to know, if you don't know already, that ions form crystalline solids. Let me get a new page for you. Ions all form crystalline solids, and this is what I mean by that. Let's draw a little box for you using a lighter color. Here's a cube, and crystals all form solids. Ions all form crystalline solids because they arrange themselves. Ions arrange themselves in a repeating pattern. That's the key. The reason why ions arrange themselves in a repeating pattern is because they are charged, and they all have the same charge. So all of the aluminum ions, they all have the 3+ charge, all of them. And all of the oxygen ions, they all have the 2- charge, all of them. So because of that, in order to maximize the attraction in between the ions, in other words, in order to minimize the distance in between the positive ions and the negative ions, they all have to line up in a pattern. So this could be the oxygen, this could be the aluminum, this could be the oxygen, this could be the aluminum. You see that? They're lining up in this pattern. And that pattern usually ends up taking the form of a cube or of some other shape. In fact, it's not always a cube. You've probably seen crystals of different shapes. A lot of times crystals are able to grow just naturally, usually underground or in some type of cave. The crystals are able to grow into all kinds of strange shapes. Every compound has its own natural crystalline shape, and the reason for that is every compound has its own ions of a particular size and a particular charge, of a particular size and of a particular charge. And depending on those sizes and those charges, the natural shape that is created by the natural pattern that these crystals form, these ions form when they become a solid, is different. Um, See, here I've shown an alternating pattern of OAL, OAL, OAL. Now, of course, you know that for every 2 ALs, there will be 3 Os. So the pattern is not so simple for AL203. For AL203, the pattern is a little more complicated and in 3D, you know. So in 3D, which I am not able to draw for you, you'll be able to get, or nature will be able to get, 3 oxygens surrounding every 2 ALs, and 2 ALs surrounding every 3 oxygens, so that you never have a case where there's an oxygen right next to an oxygen, or there's an AL right next to an AL. I mean, you may have a case where there's an AL, like always, diagonally from an AL, but that diagonal distance will be farther than a next-door neighbor distance. So that's how ions arrange themselves in a solid, and that's the reason why ions arrange themselves in a solid. Their charges are all the same for each ion. The Al ion has its charge. The oxygen ion has its charge. All right, so that's I should probably write this word for you. Sorry, the word for that repeating pattern is crystal lattice. Crystal. Crystal is that solid. Lattice is the pattern, the framework of the pattern, you know.